Let us consider the SDP dual and the alternative form that arises from there. Now, if we consider the SDP in the standard form, which was that minimize C transpose X, and convex form, which was that lambda max of f of x is less than or equal to 0, it is very difficult to derive the dual because the Lagrangian would depend on the maximum eigenvalue of f of x, and therefore minimizing the Lagrangian with respect to x would be very difficult. So we would not be able to obtain the closed form solution. On the contrary, if we write it in the LMI form, it would be of the form that f of x is negative semi-definite. Now this constraint that some matrix is negative semi-definite, it's not in the standard convex form. So how do we take the Lagrangian there? So what we will do is we will pursue this second approach where we will write it in the LMI form, but the process of taking Lagrangian will be slightly different. In particular, we will consider the matrix dual variable. So instead of a vector dual variable or a scalar dual variable, we will consider a matrix dual variable, which is y, which is a symmetric matrix, and it is associated with this constraint. So the Lagrangian in this case, which would be a function of x, as well as the matrix y, would be of the form C transpose x plus summation over I and j of fx of ij times yij. So in the same way we have taken the Lagrangian by multiplying each entry of y with that of f and summing them up, except in this case that the constraint here is expressed in terms of a matrix and the dual variable is also a matrix. And now if you remember, for symmetric matrices, note that both f of x and y are symmetric because g and fi's are symmetric and y is assumed to be symmetric. For symmetric matrices, this is nothing but the trace of f of x times y, and this is also the inner product of f of x and y for symmetric matrices. So we really are talking about the Lagrangian, which is of this form: C transpose x plus inner product of f of x comma y. And if we expand this Lagrangian, we would obtain summation I equal to 1 to n ci xi plus trace of gy plus summation over I equal to 1 to n trace of fiy times xi. So this is the expanded version. Now, interesting thing to observe here before we proceed further is that the Lagrangian is affine in x. It is also affine in y because the entries of y appear linearly in the last two terms and do not appear in the first term. So it is affine in both the primal and dual variables. There's only one other problem which has this property, that the Lagrangian is affine in both primal and dual, and that is the LP. So LPs and SDPs have this property that their Lagrangian is affine in both primal and dual variables. Of course, here the Lagrangian is derived from a different perspective because the constraint is expressed as a matrix constraint. So let's now minimize this Lagrangian. So let's minimize the Lagrangian with respect to x and observe first that this is separable, the Lagrangian is separable in x. So this would be equivalent to summation over I equal to 1 to n minimize over xi times ci plus trace of fiy plus the other terms which do not depend on x, like trace of gy. So we already know how to minimize this quantity. Basically this ci plus trace of fiy would be equal to 0, or else the minimum will be minus infinity. So the minimization with respect to xi of xi times ci plus trace of fiy is exactly, it's minus infinity if ci plus trace of fiy is not equal to 0, and if ci plus trace of fiy is equal to 0, then it is 0. So combining these, we can see that the dual problem or dual formulation becomes maximization of trace of gy subject to constraint that Ci is equal to Ci plus trace of Fi y is equal to 0, and another constraint which is coming from the fact that this is an inequality constraint and we associated a matrix dual variable. So the other constraint that will come out to be y is positive semi-definite. So y is positive semi-definite. So this is the dual of the SDP, and observe here that the equality constraint is in terms of y, entries of y, and the objective was also in the terms of entries of y, but the PSD constraint is on the matrix y. Now the first question that you would ask is that, is this a convex problem? We already have seen the LMI form, which was an SDP, and is the dual of SDP a convex optimization problem? And that is, the answer to that is indeed yes. In fact, this is also an SDP. So this is also an SDP. How is it an SDP? We can actually express it in the LMI form. To do that, let us say that the vector y is the vectorized version of y, capital Y. In other words, basically what you do is you arrange the entries of y like this. Then observe that what is trace of gy? Trace of gy is nothing but vectorized version of g transpose y, right? So it is some, you can call it as g transpose y, right? Where small g is the vectorized version of capital G. And likewise, trace of fi y can be written as some vectorized version of fi transpose y. So both of these are actually written in terms of the vector y. And then what is this LMI constraint? So y can be written as summation over I comma j of 1ij times yij. And what is 1ij? 1ij is a matrix whose ijth entry is 1 and rest everything is 0. Right? So this is the I comma jth entry. Right? So this is our y, and therefore saying that this is greater than or equal to 0. So this is indeed in the LMI form because the constraint is written as a linear combination of the variables yij times some matrices, some n cross n matrices. So all these n cross n matrices play the role of fi that we had earlier, and the constraint is of the form that, so we have minimization of G transpose Y, sorry, maximization of G transpose Y subject to Fi transpose Y plus Ci equal to 0, that is the equality constraint, and Y is greater than or equal to 0, which is the LMI constraint. So Y is the PSD, which is the LMI constraint, and this is the equality constraint, and the objective is linear in Y. So therefore, this is the SDP. So dual of SDP is also an SDP. So I hope the process of taking the dual by associating the matrix dual variable has become clear. Actually, I can further demonstrate that process by taking the dual of this and showing that we obtain the actual original problem. So let's do that. Let's take the dual of this. To do that, let us associate a matrix, a dual variable z in Sn with this constraint that y is positive semi-definite, and likewise associate some dual variables nu y with the equality constraint. Then what is the Lagrangian? So let's write it as minimization problem. So the Lagrangian will be minus trace of gy plus summation over I nu I times trace of fi y plus ci minus trace of zy. So let's maximize the Lagrangian with respect to the primal variables now, which is y. So minimum of the Lagrangian with respect to the primal variables y, and the dual variables are z and nu, is given by So let's group together the appearances of y. So we would obtain the trace of, so minimization with respect to y, trace of y times minus g minus z plus summation of nu I fi, and plus the other terms which do not depend on y, so those are plus C transpose nu. So again, this is in linear in y, and therefore its minimization is very simple. We just set this coefficient to be 0. So we obtain therefore the dual form, which is maximization of C transpose nu subject to constraint of the form that summation of fi nu I is equal to g plus z, and we of course have the constraint that z is positive semi-definite. Now, is this the original problem? Let's massage it a little bit. Let's write this problem as minimization of minus C transpose nu, and z is equal to summation of fi nu I minus g, and z is positive semi-definite. Now here, let us replace nu with minus nu, so we can obtain that. So what we can do is simply replace nu with minus nu, or we can say nu equal to minus x. So we can obtain minimize C transpose x subject to constraint of the form minus g minus summation of fi xi is greater than or equal to 0, or positive semi-definite, and this way z also gets eliminated. So this is exactly in the original form that we started with, which was that g plus fi xi summation of fi xi is negative semi-definite, right? And this was our f of x. So we have seen that we have derived the dual of SDP, and by again deriving its dual, we have seen that we get back to the original problem. So this is almost always the case with convex optimization problems. If you derive the dual of the dual, you get the same problem, but it does not necessarily happen for non-convex problems.